Tyler LeBaron, welcome to the show.
All right, thanks, brother.
Oh, I'm pumped, man. So for the people hanging out with us, give us a little recap. We're here at the Regenerative Medicine Conference. Share with us a bit about what your day has looked like so far in terms of your nutrition and your training.
Yeah, so let's see. Yesterday I ran 13 miles, and then I ate lunch, and then that's all I ate. And then I was like, well, I got to go running. So this morning I got up. I only slept 4 hours last night. Actually, I only slept 4 hours the night before too, because I've been busy and the emails, and I'm traveling, and the Florida time change and everything. So I only slept like 8 hours in the past 2 days. And then I get up and like, well, I got to get my run in, and so I ran 15 miles. And then I was like, oh my gosh, I got to get back and shower and get ready to go because I'm presenting. So I went and jumped on stage, presented, and then, all the energy and everything you have to have. And then, of course, you and I went out to the gym and goofed around over there. That was fun.
Yeah.
And I just finished eating lunch, so now I'm ready to take a nap. So if I start dozing off, you'll know I'm just feeling comfortable.
That sleepy insulin spike post-lunch. Yeah. So basically, fasted for 24 hours. You have ran 28 miles in the past 2 days.
Yeah.
You presented at 10:30 a.m. on molecular hydrogen at the Regenerative Medicine Conference. So approaching that 24 hours fasted mark. And then we went and filmed a video that you guys can check out where Tyler's banging out one-arm pull-ups in his suit. The guy's just a beast. He's got where's your deadlift at, just for people to have?
So 420 or so. Yeah, on the straight
420-pound deadlift on the straight bar.
Yeah.
Do you know your hex bar?
That was 450, I think.
Yeah.
455.
And then marathon times. Like what?
So I'm just getting back into the marathon. So I'm training again. I haven't ran one since 2011. I looked and I'm like, oh my gosh, that's so long ago. I got to do that again. So I ran in 2011, and that was my third marathon. I ran at 2 hours and 30 minutes.
What does that break down to?
So 26.2 miles is a 5:45 average mile pace.
5:45 miles.
Yeah, I was booking. Yeah.
I ran like a 5-minute and change mile in my senior year of high school. We had to run 2 miles in under 12 minutes.
Okay, yeah.
And like the first one was, I think it was like 5:18. And I remember the whole second mile, I felt like I was going to simultaneously crap my pants and throw up.
That's the feeling.
You did that for 26.2 miles.
Well, no, not the whole thing, but that's you got to have that feeling so you can. I know what you're talking about, man.
Man,
that's what it takes.
I'm impressed. So basically, you are a beast. You're putting up some amazing statistics, and in this episode, we're going to talk about some of your secrets. You run the Molecular Hydrogen Institute, so you're the leading researcher in all things molecular hydrogen. What's available?
Well, I don't know that I'm the leading researcher. I'm a researcher trying to, I'm doing the research, I'm getting involved, but really one of the only ones here in America. And it's so new. Most of it's coming out of Asia. So I collaborate with a lot of universities, institutions out there. And so Molecular Hydrogen Institute, we're a nonprofit. We don't sell or recommend or do any product stuff, but it's just a platform so that I can help research and collaborate with other universities here in America and around the world and get things going, get the education, the awareness out about what we're doing.
Yeah, well, I was enjoying your presentation so much. I would love to get a copy of those slides afterwards because the number of studies that you were including on the benefits we're seeing with molecular hydrogen was fascinating, and I plan on us diving into some of those on this podcast. For the average fifth grader who's listening in, explain what molecular hydrogen is.
Yeah, that's a good place to start. So first we talk about molecular hydrogen. We are talking about a gas, H2 gas. And so going back to your I guess high school chemistry, right? Hydrogen is the number one on the periodic table, right? So it's the first element in existence, and that's hydrogen. Now the hydrogen atom is very reactive, and it combines rapidly with another hydrogen atom to form diatomic hydrogen. Di meaning two, not like death. But
so it's a little bit less reactive.
Right, yeah. Is that? Yeah, well, yeah, it's basically essentially inert. When it combines, because each atom has one electron, they combine, and then you fulfill the valence shell electron. I know we don't need to go into that, but it makes it so it's not reactive anymore, essentially, and now it's stable, and that's how we find hydrogen gas, and that's that is the upcoming alternative energy source, right? It's 3 times more energy dense than gasoline. And it's just interesting because now we're finding it as like part of alternative medicine, if you will, like just alternative, kind of play on that word. But we're seeing it has a biological therapeutic effects.
And if you had to categorize it, is it more of an antioxidant? Is it more of an adaptogen? How would you categorize molecular hydrogen?
I tend to like the idea of more adaptogenic, redox adaptogen. In fact, I'm just publishing a paper in the Canadian Journal of Physiology and Pharmacology. We talk just about that, the redox adaptogenic.
You brought that up, and that caught my attention during your presentation. what is redox?
Yeah, so yes, yeah, good. Yeah, so redox meaning oxidation and reduction, right? So in like just like a battery, you have a positive electrode and a negative electrode, right? And you have to have both of them. That's what the electrons are going to go through, type thing, and make the light bulb go. So you have to have both of that, and you have to have both. You can't just have just reduction, right, or just oxidation. You have to have both. And so in a lot of ways, like your cells, your body, your organs, it operates like a battery. You have to have both oxidation and you have to have reduction. And oxidation reduction, or it is called a redox, right? Mm-hmm. That's what it means. So you have to have this redox homeostasis. And so you can't have too much oxidative or else you have oxidative stress, right? You have too much going on, and that oxidative stress, of course, like when you cut the apple in half and it turns brown, you start to see, things that rust. That's all oxidation.
And would that be considered like a positive charge inflammation in the body, like too many positive charges that aren't being neutralized, or am I misspeaking?
Yes and no. It's kind of some misnomers. Most things that are oxidative are not necessarily positively charged.
Okay.
So I know that's going to be kind of confusing because we get this idea in our diagram, antioxidant electron, now it's positive. It doesn't really work that way. Most free radicals are actually negatively charged, like the superoxide anion radical is a negative charge. Many radicals are neutral, like nitric oxide, hydroxyl radical. These are neutral. Hydrogen peroxide is an oxidant, that's neutral. So it's not about that, it's about the how many electrons are in the shell, basically, whether it's going to, if it's paired or not. Because they want to be paired. So if it's just a single electron, it's going to be like really reactive. But it's paired, it's like we're talking about hydrogen. When hydrogen pairs another hydrogen, it makes it stable. And so when you have too many, like when we breathe oxygen, sometimes that oxygen can be made to be unstable. For example, if it accepts an extra electron, then it becomes this radical, superoxide anion radical. And
what makes that happen?
So so actually if we go through metabolism, maybe this will kind of help. We kind of break down what happens when you eat your food from the very beginning. When you eat your food, what happens? So you put the food into the mouth, and then it gets digested, broken down to your simple, carbohydrates and your protein, your amino acids, right? It goes into the bloodstream, and then let's say your carbohydrates, that's going to be broken down to glucose, and that's going to go into the cell, and it's going to go through a process called glycolysis, right? And that breaks it down to really small molecules, and you get a little bit of ATP, the adenosine triphosphate, your energy, right? You only get about 2 molecules of ATP when you do go through glycolysis. And then you form this molecule called pyruvate. And when there's no oxygen there, then pyruvate gets metabolized to lactate, or we get lactic acid. That's that whole side, right? Mm-hmm. But when oxygen is present...
Like the lactic acid burn when you're working out, you're not getting enough oxygen.
Yeah, which is just a correlation, because there's no such thing as lactic acid and it doesn't cause burn. We'll talk about that next, maybe.
Yes.
But... So when the pyruvate, when the oxygen is there, it can be shuttled into the mitochondria through the pyruvate dehydrogenase complex, and I'll try to keep things really quick. But when it goes through into the mitochondria, then it's
which make our energy,
right? It's going to continue to get broken down, and so you have glucose is 6 carbons, right? Or C6H12O6, so 6 carbons, 12 hydrogens, and 6 oxygens, right? And when it's broken down to CO2, and that's why you exhale out. So everything you exhale out, you're exhaling out the CO2 from your food. And so when it goes through the glycolysis and the mitochondria, you're basically breaking down to just CO2, which is a fully oxidized molecule. And when it does that, the electrons that were on that glucose molecule get transferred onto like NADH and NADPH and different molecules, and then it goes through what's called the electron transport chain. And oxygen is at the very end. It's on complex 4, and it's very oxidizing. And so it takes the food from over here, the electrons, and tries to take the electrons from the food and drives all these metabolic processes, all the enzymes, all the enzymatic steps, the electron transport chain, and just brings the electron to here, and then to here, and then to here, and then to here. And every time it does that, it makes a molecule of ATP. But oxygen is driving the entire thing. And finally, when the electrons with some hydrogen ions, protons, when they meet up with the oxygen, you form water. So we make water. It's called metabolic water. We make water in our mitochondria, right? And of course, that's why camels can actually survive a lot longer, because they make a lot of water when they store so much fat in their humps.
This is fascinating. So what you're saying, if I'm understanding you correct, and I'm sure I'll be corrected many times in our conversation, but I like that. When we eat food, a lot of people mistakenly believe that we're processing some of it and then we're releasing it as urine and feces. What you're saying is, yes, that's happening, but most of it is actually being released as waste through
CO2.
The air we exhale.
That's
CO2
right. Yeah,
in the form of CO2.
Yeah, that's right. Yeah. So and everything is working fine. Then the transfer of electrons is in perfect cadence with the consumption of oxygen. Oxygen comes, it comes right to the complex 4, and then It combines, and then you form water, and then there you go.
That makes sense.
But when you start to exercise, or maybe you have some compromised mitochondria, or you just you're in bad health, or maybe some pesticides, some toxins, whatever it is,
right.
all these things can perturb that process. And now maybe oxygen is going to come over earlier, like a complex 1 or a different complex or something, and it's going to take that electron earlier. Well, if it does that, it can't form water because it's too early in the complex. Instead, that oxygen is going to accept one electron, a single electron reduction, to form a superoxide anion radical. Now that superoxide.
So pause 1 second.
Yes.
Just in this scenario that you're describing, you're saying if the individual if their mitochondria are not functioning properly, that whole electron transport chain will not behave the same way it will in someone who is healthy, and in that process they will make less energy. They'll almost go into like survival mode.
Less energy.
They'll make less energy, and it sounds like potentially become dehydrated at the cellular level, because their body is not making as much H2O as it would if their electron transport chain and energy production process was functioning normally.
That is an interesting, I'd have to think about the whole dehydration process, because you are making metabolic matrix water in there.
It's part of the reason that I look at the Bun to creatinine ratio. We're trying to figure out where is cellular hydration, and it's often, that Bun to creatinine ratio is often quite high in individuals whose mitochondria, whose energy production. No, the Bun to creatinine ratio is high if their mitochondria aren't working properly, showing cellular dehydration. Like there's a connection there, and we have this idea also that like our hydration just comes from what we put in our mouth, and you're saying no, our hydration is also dependent on how well our mitochondria work.
Yeah. I mean, there's a lot of those factors, and that all adds up. We do lose a lot of water through our exhalation
as well, right?
And so
part of why we're dehydrated in the morning,
yeah,
provided you're not sweating all night.
Right. So all that comes into play. But you're right. When you have the compromised, mitochondria, any of that process, or even the food that you're eating, when it's not, good, you're going to produce more of these free radicals, and that. But it's interesting because
the more you eat, the more you work out, the more free radicals you're making.
Yeah, just by definition, because as you eat more food, you're going to have to breathe more oxygen to consume that. As you exercise, you breathe more oxygen. So just by the sheer default, as you increase, you're going to be making more free radicals. So exercise by definition drastically increases free radical production just because you're producing more.
And especially if you're exercising at a level like you are, where you're running 13 miles yesterday, 15 miles today, you've got a 400 plus, 450 pound plus deadlift. If we're using the hex bar, you're banging out one arm pull-ups to activate those type 2B muscle fibers. Where does molecular hydrogen fit into this? And how do you address that increased free radical production and protect your body?
Well, okay, so if we go back, because to your original question, is hydrogen gas more of this adaptogen or this antioxidant, right?
Yeah.
And so as we understand that free radicals can be produced in the mitochondria like that when it gets compromised, but at the same time, we have to remember that the production of free radicals always occurs, and it's regulated, and it's very important because, like I said, like the whole battery idea.
It's not a bad thing.
It's not a bad thing. We have to have it.
Right.
Those free radicals is how we communicate do cell communication. It's a redox signal transduction, right? Yeah. It's really important. And
I'm like,
yeah.
I'm going to do that a few times, and I won't know. I'm not that, but yes, I got you.
I love it. No, but so then what happens then is these free radicals are produced in a very small amount, and they're utilized immediately because then they oxidize as a sulfur, whatever they do, and then they immediately.
What does it do with sulfur?
So, for example, like if you have a residue like
and I'm curious because so many people who have mitochondrial dysfunction, poorly functioning mitochondria, their energy production process has been compromised for any number of reasons. They're often deficient in sulfur and glutathione.
Yeah,
B vitamins and a bunch of stuff too, but that was why I honed in on
because
sulfur.
the mitochondrial electron transport chain, that has a whole bunch of like iron sulfur clusters, and those iron sulfur clusters are the whole important step of carrying and transferring the electrons into the risque iron protein cluster, like all this stuff. Sulfur is critical in all that. So your amino acids, methionine and cysteine, are what carries that sulfur, and you make glutathione from that, and so you have you form a disulfide bond, and that's a very reducing bond basically, so it can donate the electrons and to scavenge radicals and things. And so what can happen is when you produce some free radicals, it can oxidize something. As you oxidize the bond, it's gonna change, and now it's gonna be active. And so when it's active like that, that can activate transcription factors. So transcription factor is something that can bind to the to the DNA and then cause transcription or production of various proteins and other beneficial things or negative things. So that's how free radicals work. And so in a healthy individual, you make water here, you make a little bit of free radicals here, and those free radicals do the little thing. They oxidize these things. You get good benefits. You're able to live and function. As soon as they oxidize whatever they can oxidize, you're going to have like superoxide dismutase, and they'll convert superoxide radicals to hydrogen peroxide. You have catalase, glutathione peroxidase, all of these to quickly get rid of the oxidants, so they maintain at a certain concentration and a certain location. Now, when you're in the compromised position,
what would you say is like the reason that it's so important for us to maintain that balance of redox?
Yeah, because as soon as you start producing too many free radicals, as soon as you start increasing that production of the superoxide too high, so now your body can't clear it. You've already oxidized a whole bunch of your glutathione, right? You've oxidized all these things, and you're just shooting out high levels of superoxide. That superoxide starts to oxidize other important things. It can also go through what's called the Haber-Wade reaction, the Fenton reaction.
What was that? The Fenton reaction?
Yeah, so basically you have like iron that's somehow available because superoxide can damage the iron-sulfur clusters. It can release iron out, and then you're going to have superoxide can reduce iron 3 to iron 2. Iron 2 will then react, and then it reacts like hydrogen peroxide, for example, and you form hydroxyl radicals. Now that's when you're in serious problems.
Right.
The hydroxyl radicals.
And this is part of what's happening with...
Yes, in the mitochondria, in the body, and you can form hydroxyl radicals like radiation, ionized radiation, different things. We'll talk about that, but there's these hydroxyl radicals are so toxic because they react so fast. They react with pretty much anything indiscriminately and just immediately, and so they damage your DNA, your RNA, your proteins, your cell membranes. They induce radical propagation, which means it's going to oxidize a lipid. Then now that lipid's oxidized, it'll oxidize another and another and another, and just so on. And it's
like
just
a domino effect.
It's just death. Yes, exactly. So that's what we have to regulate the superoxide production. It can't be too high. We need to have it at a certain level, and if it gets out of whack, it's going to cause all those issues. Okay. Now, when you exercise, you do produce more free radicals. So you are oxidizing more. But what happens is your exercise only lasts for a couple hours or something, Well, it depends on how far you run or what you're doing, right?
Everyone's like, a couple hours.
Well, I'm saying, like a marathon, right?
Yeah, if you're running 15 to 26.2 miles.
Yeah,
sure.
Exactly, right? So what happens then, you get this transient spike in these free radicals. Your body's like, oh my goodness, this is not good. This is too much. And so it activates it. It oxidizes these sulfur bonds, if you will, and then it activates what's called the NRF2 pathway. It's a transcription factor. NRF2 comes and it binds to the ARE antioxidant response element or the electrophile. Anyways, but it binds there to the DNA, and then you start this production of your cytoprotective proteins and enzymes. Over 200 proteins and things are regulated by the NRF2s. Detoxification, antioxidation, and all these beneficial things. So by exercising, you get the transient increase in ROS production, but then you're done exercising.
ROS
so now,
being reactive oxygen species.
Yes, sorry, thank you, yes. And then so you get the transient increase, now you're done exercising, and then you get this increase in the NRF2 activation. Now you have higher levels of glutathione. So athletes are going to be way better at basically being protected against oxidative damage because they have higher levels of antioxidant enzymes and proteins compared to the sedentary counterparts.
They have many more workouts that have created that adaptive response.
Exactly.
Right? Spike free radicals, then the body adapts and then neutralizes it, and it gets better and better at doing that.
Right.
Probably ramps up endogenous from inside the body glutathione production, which is like our master factor. It's like this person needs more because they're training 6 days a week.
NRF2 increases glutathione and superoxide, dismutase. So now what would be the consequences then if the athlete ran not just for an hour or 2 hours a day, but ran, say, 24 hours a day? Right? It would just
no time to adapt,
total
right?
constant increase in ROS production.
Right.
Well, that's what a disease is. It's just many diseases are just consistent, constant, onslaught of this ROS. So yeah, you're getting that trying to increase the glutathione, but you're just oxidizing.
And the body just can't keep up.
It just can't keep up, right? But that's what exercise, you get the transient spike and it goes back down, but you do get the upregulation
sort
of
of like what I was talking about yesterday with like the chronic sympathetic overdrive. Like the body is just constantly getting flooded with free radicals from an onslaught of toxins, stress, elevated cortisol, radiation, a whole bunch of stuff.
When it's chronic like that, that's always going to be a problem. That's always going to be a problem.
And then, so how do we deal with it?
Yes, exactly. So now we have that as a backdrop, right?
Yeah.
So now we look at molecular hydrogen. So again, as we said, hydrogen is just very, it's a very small molecule. This is really important to consider because when we talk about cellular bioavailability, what dictates its benefits is first it's got to get into the cell. And so number one, the size. The smaller
Can't
it
fit a
is,
Saint Bernard through the cat door.
absolutely, exactly, yeah. So hydrogen is the smallest molecule in the universe.
Right.
Okay, it's smaller than oxygen, so it's got that taken care of. It's also neutral, so it doesn't have to go through any ion channel or something like that. It's also non-polar.
Non-toxic.
Of course it's non-toxic, exactly. But all these physical chemical properties of molecular hydrogen allow it to easily diffuse quickly into the subcellular compartments of, say, the mitochondria, the nucleus, and everything, where all these free radicals are being produced at. And now that's where the magic happens.
Yeah, tell us.
What does it actually do once it enters the mitochondria? Once it enters into, say, the endoplasmic reticulum and the nucleus?
Yes. So you were talking a little bit about that in your presentation, and I want to dive into what's happening in the endoplasmic reticulum, in the ER. We'll call it the ER.
Yeah.
But just to comparison, and tell me if this is accurate. Let's say my fist, in terms of relative size, represents like coenzyme Q10.
Okay.
And therefore, because of its relative size, some of its difficulty in getting to the intracellular space. Molecular hydrogen would be like the tip of my thumb. And in part because of that decreased size, it's better able to get in and protect the mitochondria from that free radical onslaught that you were describing earlier.
Right, yeah. I'm not showing the relative
Am I making
size.
stuff up?
Yeah, no, that's right. I mean, if we look at the diameter, so coenzyme 10 has a 1, 2, trying to just visualize. I mean, but I guess it doesn't really matter.
Close enough,
but,
right?
But like vitamin C, for example, is 176 grams per mole. That's the weight, 176 grams per mole. Versus hydrogen gas is only 2 grams per mole. Right? So it's just a lot smaller, right? It weighs so little.
It's like trying to take an empty jar, and fill it with big stones. You're going to have a ton of space left over versus like sand. You're able to fill the jar.
It's very pervasive.
If a full jar represented proper free radical, proper redox potential in the body, elevated redox potential.
But that's a good point, because when you look at like CoQ10 or vitamin C or different things, well, if you're getting all these free radicals that are occurring like within the mitochondria and that inner mitochondrial membrane, well, first off, very little things can cross the inner mitochondrial membrane. There's very few things that can actually do it. There's like 5 things that are like the main things that can. Everything else is like essentially impermeable, because that's where the proton gradient is.
What can cross the mitochondrial membrane? I have to ask.
Well, usually like malate, for example, there's an actual shuttle that goes through there, right? Small molecules like oxygen gas, because that's how we can use it. Hydrogen gas can do that. So all those types of things can do it. But most other things have to be transported in there. Because there's just, and if it's not transported in there, essentially it's not going to get through unless it's small, like hydrogen or oxygen.
Right.
So it's a very impermeable. So you're trying to get like vitamin C there or other things, it's very difficult. So like CoQ10, well, that actually goes to a different mechanism to be able to get there. Transporter systems are synthesized. There's a whole bunch. It's a
lot of work and intermediary steps that also require a biologically healthy individual. Like
to be able to do
everything's able to do that. Yeah, it's able to happen.
Well, hydrogen gas. No problema. Va a ir por,
and we're going to take all of this and apply it in a practical way for you guys, for your workouts, just for overall health, avoiding chronic disease. So we just want to give this foundation to them of like the science, so that they understand why they're doing what they may want to do.
Right. No, absolutely. Well, and it goes to your question too about the whole idea of this, the redox adaptogen thing.
Yeah.
Because hydrogen gas can get in there. And where it's going to work, its magic, if you will. Well, it's classic. So if there's too much oxidative stress going on, that's going to reduce that. It's going to help decrease that amount of oxidative stress. And so in that case, it would act as an antioxidant.
Right.
Now, an antioxidant, by definition, there's 2 definitions. The chemical definition, which is simply an electron donor. It's a terrible definition because that's not how the body really works. A better definition is simply an antioxidant is something that improves the redox status of the cell. So by that definition, exercise is an antioxidant. Many things can be an antioxidant in that case. And hydrogen gas, that's how it works. It simply improves the redox status of the cell, whether that's to increase oxidative processes or whether to decrease oxidative processes. And that's why I'm saying adaptogenic.
That makes sense. And I mean, we're starting to realize that let's take the classic example of vitamin C, one of the first molecules that people referred to as an antioxidant. We're now realizing that is actually a pro-oxidant And its antioxidant benefits come from what happens later, the
Right.
signaling pathways that are turned on from it, correct?
Yeah, most things are actually that way. Most things that are good for you are good for you probably because they're slightly toxic.
Yeah.
All your foods that you eat, the polyphenols and these types of things, that they're slightly toxic, and so they actually are turned into pro-oxidants, and they activate the various transcription factors. They're not simply passing scavengers, but are intimately involved in the redox sensitive pathways.
And this is a fascinating mini tangent. We won't go too far, don't worry. But with the popularity of like Dr. Stephen Gundry's plant paradox, where he's now pointing out all of these toxins in plants.
Yes, that's right. That's exactly right.
When you look at that in the context of what these toxins are actually doing, of course the dose makes the poison, but in tiny amounts, we're seeing most of the things that signal beneficial adaptations in
Right.
the body are toxic.
And that process is called hormesis.
Right.
Hormesis, and it's a hormetic effect. Exercise is a hormetic effect, and my paper talks about all of this. So that is what we're seeing more and more. The body operates on that, and so this is interesting because you talk about homeostasis. Talk about the thing that's going to kill you the fastest, when which is sitting on your couch, keeping it at
Being
exactly
comfortable and
25
alone.
degrees Celsius or
Yeah.
70 degrees, right? Yeah, comfortable, just sitting there and enjoying, right?
Yeah.
You will get atrophy.
Fat,
All this.
fat and happy. You know?
Yeah, right. Exactly. Just like it's amazing. That's what happens. But it's the stress of the body. The stress of the body, the hormetic effects that's going to make us longevity and live longer and be healthier and stronger and so on.
I love it. And so before we move on to some of your training and some of the ways that you break through plateaus in both your running and your lifting, how do you use molecular hydrogen?
Well, we didn't. Let me just say a comment about hydrogen gas. A couple of the benefits, because we didn't quite say. So hydrogen gas is able to activate. This is really cool. It's able to actually activate the NRF2 pathway. That's one of the things it can do. We've seen this pharmacologically blocking the NRF2 pathway.
So NRF2, explain what that pathway does.
Yeah, again, so that the NRF2, that is a transcription factor that when it gets activated goes down into the nucleus and binds to the DNA. When it binds to the DNA, it induces the transcription, the production.
Making your proteins and making sure
of
those proteins.
glutathione, right?
Okay,
Glutathione,
okay.
all your antioxidant enzymes, your detoxification enzymes. NRF2 is a master regulator of phase 2 enzymes.
Okay.
And that's your antioxidation and detoxification enzymes. NRF2 is the king when
Okay.
it comes to all that. And you want to have this, and you don't want to have it constitutively activated either. Meaning you don't want to just chronically stimulate it, like we talked about. Anything chronic, whether it's a disease or something good for you, is bad. You can't have that. If it's all the time, you're not getting the benefit.
So an example of chronic NRF2 activation might be someone who's megadosing curcumin and green tea polyphenols and those types of things, and they're just taking them all the time indiscriminately. They're not cycling off.
Yeah, for a long time, right?
Right.
Then you get to the same idea of I'm going to go run 24 hours a day.
And this is also part of the reason that you recommend pulsing molecular hydrogen if you're using it.
Right. Yeah. Some of the research that we have is when there's a continuous administration, the benefits are essentially eliminated. So, like when we put like the animals in the cages and expose them to hydrogen gas, we actually see really good benefits, and then they start to go away and diminish, and then they're totally gone.
So it activates the NRF2 pathway. What else does molecular hydrogen do?
So it actually activates. There's well over 200 different biomolecules that it activates. Lots of transcription factors like NFAT signaling, which is really big into inflammation. That's a really big key.
Which one was that?
NFAT signaling.
Okay.
Yeah, and this and of course NFKB, which is another transcription factor to activate by TNF alpha, and there's a whole process loop with reactive oxygen species and inflammation, and they interconnect and produce the other and so on. So hydrogen gas is able to modulate, regulate both of these processes, because just as we need free radicals, we also need inflammation.
Right.
And this is a critical thing that we need to consider. Inflammation is like so important. Those pro-inflammatory cytokines, the interleukin 6, interleukin 10, well actually interleukin 10 is anti-inflammatory, but all these cytokines are extremely important. And if we don't have a good inflammatory response, we're not going to heal. We're not going to recover very fast. We're not going to get stronger and better. We're going to be sick. We're going to get all these things. So that's the problem with aging. Just as aging causes redox dysregulation, where you have too much oxidative and not enough oxidative power and potential going on at the same time, the same thing happens with aging. So when you get older, you have this chronic pain, chronic back pain, your knees hurt, arthritis, all these things, but you also get sick really easily. So you have a bad immune system and you don't heal very well. So you have like low-grade inflammation chronically all the time, and then you have a slow response, so you're not able to get the benefits, right? And so that's a whole dysregulation, and hydrogen gas is able to regulate both of those. And it's interesting, like even in your athletes, we're looking at like when you exercise, your muscles can produce these myokines that are like the inflammatory markers and mediators. And when you block that effect by, say, ibuprofen or other NSAIDs or anyways, you can essentially blunt the benefits of exercise training. Just like you can blunt the benefits of exercise training if you take high levels of antioxidants, exogenous antioxidants, high levels can blunt the benefits of exercise training. Well, high levels of these anti-inflammatories can also blunt the benefits of exercise training. And
it's very interesting.
And when you and potentially, there's one article on using arachidonic acid, an omega-6 fatty acid, which are like, oh no, stay away from omega-6. It's just down omega-3s. Well, this study actually, they supplemented with omega-6 fatty acids, and that's going to produce more of the eicosanoids that are pro-inflammatory, and they got good benefits, stronger. They were able to actually improve and get better because they had more of that inflammation going on. And so that's like totally contradictory, right?
There are products, supplements for hypertrophy, building muscle, that the main ingredient is arachidonic acid, or I'm mispronouncing it.
Yeah,
but
No, that's right, yeah.
Yeah, and I'd even tried it probably 15, 20 years ago. I was curious. Like when I didn't really start putting on muscle until like my junior, senior year of high school. And I was like, that's when I started creatine and some of the things, which I'd like to talk about your creatine protocol too. But I remember experimenting with a supplement where arachidonic acid was like the main ingredient. And within a week, I was like, I was getting bigger.
Yeah.
I got bigger faster, but I was also very inflamed.
Yes.
I was losing flexibility, mobility, and playing soccer at the time, so that was concerning. I had to get off of it. I just wrote the company and was like, "Hey, I can tell it works, but my body hurts." And they're like, "Send it back. We'll take care of you." But there are supplements, and it does work for some people.
And if you do it right, we're talking about like fasting and intermittent fasting and the whole autophagy things and cycling, all of this that allows you to optimize and really biohack the body. And hydrogen gas is one of them because it helps to regulate the entire process of the free radicals, antioxidant balance, as well as the inflammatory response.
That's so cool. How do you apply molecular
so
hydrogen?
There's several ways. Yeah, several ways that it can be done.
You personally?
Well, I do several things. I can't divulge all my secrets. No, I'm just kidding. I often just water is the easiest. So you have different effects. So I often just have water that contains the hydrogen gas.
You drop the tablets in?
That's one of the tablets are really easy. You can just drop a tablet in.
Or you have a machine.
I have several machines that you can even just have a tank of hydrogen gas and you can infuse pure hydrogen gas in there. Oh. You want to make sure the hydrogen gas is pure. So even some of the machines out there, well, you have to be cautious because there could be maybe some, maybe if the electrodes aren't totally clean, you even drinking that water, all of these things you need to consider because it could be harmful, right? So you have to look at all of that. And then of course just inhalation of the hydrogen gas, which is another excellent way to administer hydrogen because it goes right into the bloodstream and you're able to get that. Now the next question of course is, well, then which one's better? Which one? Well, we really don't know. It almost seems that in some cases for these acute diseases and people who are just really bad, inhalation maybe it's a better way just because it's going to be really fast. It's going to get into the actual cells faster. Whereas drinking hydrogen water, the clinical studies, it's going to start to change gene expression, right? And because it's interesting because we always talk about how we are what our genes are, right? But that's not really accurate. It's really the expression of our genes.
Right, the epigenetics.
And the epigenetic and all this kind of stuff. And hydrogen gas, because it can help regulate gene expression, that's going to benefit us in giving those favorable expressions of our genes that we want for optimal health and longevity.
That's pretty cool. So, have you taken molecular hydrogen today? While you're traveling, probably.
But I did, yeah.
But you did? Okay.
I took some of the hydrogen water. I actually just used some of the tablets they had at the conference. I just threw them in there. Like, well, this will be good. Get me some.
Did you do it before your run today?
I did also before my run. Yeah.
Okay. How many tablets do you typically do?
Well, I don't do it all the time. Sometimes I forget. I don't have a problem. You know what I mean? So I don't really notice a whole lot of effects.
You don't see differences in your times?
Well, if I'm competing or something like this, or if I'm like just pushing it, then I do notice that I'll have a faster recovery time. But if I'm just going to go for an easy 15-mile run or something, and I'm just...
So it depends how close you are to your threshold where your body's not able to recover.
Yeah, the further away from homeostasis, the further I am from homeostasis. So if I'm majorly sleep deprived, which I have been, why
are you not sleeping?
Yeah.
we were done quite early yesterday.
Too many things to do. Like, I gotta get this article done. But yeah, the further you are from homeostasis, the more effect it seems that hydrogen gas has. And I think that anecdotally, of course, I'm not an anecdotal person, but just trying to look at things, so maybe I have some empirical way of looking at what's going on. People who have more serious issues and they're further away from homeostasis, they tend to notice the hydrogen to a much greater extent and a lot faster than people who are just healthy. So if you're just totally healthy and you just take the hydrogen and you don't really do anything extreme, you may not notice a whole lot. But if you take like the dose of hydrogen and then you like push yourself in a workout, you might find like, dude, I used to do like 4 sets of 10 of 25 pulls, but now I can do like 5 or 6 sets or something. Like you just the bouts of exercise, you get more faster recovery, and the next day you're like, I'm not so sore, like I'm ready to kind of go again.
Yeah, to echo what you're saying, I've observed the same things. Like Keith Baxter, who got him and his wife were accepted into the Trucy case study, which I know you're not affiliated with any companies. I'm just telling a story. His wife trains for triathlons. And within a week of her drinking the molecular hydrogen water, she was seeing improvements in her run, swim, and cycling time with no changes to diet or her training regimen. Like just doing the same workouts that she was doing to prepare, they were getting easier. There was increased time to fatigue.
Just by drinking the
water.
water.
Delayed onset of fatigue just by drinking the water, which is cool because you have to drink the water anyway to stay hydrated. And Kyle, who he filmed a bunch of videos with us, he came to Biohacking Week. He's a buddy of ours. He's had some Lyme disease and other chronic things going on, and he breathed the vital reactions machine, the 7% machine at my place when we were in between shooting. And he's like, he looks at me after about 40 minutes and he goes, "What's in this?"
Is that right?
He's like, "I feel fantastic." He's like, "I'm like euphoric," right?
Yeah.
So it's very interesting, and it is reflecting and confirming some of your theories.
And some people seem to be more sensitive than hydrogen. Some people take it and they're like, they feel it literally within 30 seconds. It like hits the brain. They're just like, they just noticed something, And it's really quite interesting. But yeah, it's great for the athletes. And we see like in one of the first studies is done on elite soccer players, which is cool. So elite, it is hard to improve performance in elite athletes. We got to understand that. Like
you got to fight for like 1 or 2%.
Yeah, exactly. It's really difficult. So a lot of the supplements on the market, when they look at the studies, they just used healthy, active subjects. And when they test those same supplements in elite athletes, no performance benefit. That happens over and over again. They're already like so primed to the top. Well, in this study, they looked at exercise fatigue and lactate production, and they found that the administration of just drinking hydrogen water is what they did in this study, helped to improve the endurance, so they didn't get fatigued as quickly, as well as they decreased the amount of lactate being produced. They had lower lactate levels. Which suggests, because remember, if you go through that pathway we talked about earlier, you can rewind and study. You'll have a quiz after. But when there's no oxygen available, right, because you're pushing yourself too high, your energy requirements are too high, and the oxygen's not ready, you start to produce that lactate. Well, in this case, because the lactate levels are lower, well, that could be because hydrogen gas has all these beneficial effects in the mitochondria, right? Prevents the oxidative stress, which would compromise the mitochondria, improves mitochondrial efficiency. So now the mitochondria can work better, so you can utilize that oxygen better. By utilizing the oxygen better, you don't have to go anaerobic. You can maintain aerobic exercise. That way you're not going to produce the lactate. And so we see these effects in the mitochondria, increasing ATP production and things.
That's so cool. What are you most excited about for the future of molecular hydrogen?
A couple areas. One of them, we're seeing some pretty powerful results when it comes to like dementia, neurological diseases, and Alzheimer's, and simply just drinking hydrogen water or inhalation, which seems to really.
We've got my dad drinking it, and I want to get him on the tablets too.
Yeah. Get in. And inhalation could be a really great way to go. Just another study that came out. It was a really small study, but they used a nuclear magnetic tensor imaging. Basically to look at the strength of the neuronal bundle with hydrogen inhalation, and you can actually see the changes that are taking place. And it's a small study, but it was really powerful. The improvements, actual improvements, not just the slowing the decline, but actual improvements of these people.
We'll include some of these in the show notes, so people that
Perfect.
really want to nerd out. The people that have made it this far in this episode are certainly high level or just nerd out on this stuff and are learning like crazy. But we'll include those studies so that if you want to dig deeper, you guys can check those out.
Yeah, so we look at the neurological aspects. That's one big thing, because again, this is safe. Everybody can do it, because at the worst, it's not going to do anything for you.
You're right. Yeah.
Right? And at best,
that's the definition of asymmetric risk: low downside, very high upside.
And that's really why I'm so passionate about it. It's not because we have thousands of clinical trials proving this works as the panacea for all. We really don't know. We don't. There's only 60 something clinical studies, a little more than that, probably a bunch underway, and just over 1,000 scientific publications. So it's really kind of green science right now. But the risk to benefit ratio is so amazing that I was like, yeah, let's study this and let's get the word out and let's try it. Let's see if it works. And the promising results from going from preclinical to clinical studies is just really, really great. So when we're talking about disease states, we're talking about prevention for just overall health and longevity, well-being, that kind of stuff, and then exercise performance. Those are like the three areas that I'm most excited about molecular hydrogen.
Yeah, me too. And that's part of the excitement that I have for the TRUCY case study, because the requirements are monitoring certain biomarkers and checking in over time. So you're taking prior to any administration of molecular hydrogen, and then you're tracking yourself over time in a number of different areas, essentially to make it like a grassroots clinical trial. Now, it's not as regimented and there's not as much oversight, but it's still able to contribute to some of the anecdotal benefits of molecular hydrogen.
That's often how things start, when there becomes so many anecdotal testimonials, and we try to do case reports and try to analyze things and do the best we can, post hoc, and try to see how much of that placebo and so on. But it gives an idea. So all of a sudden we start seeing, man, everybody who has, say, arthritis, or everybody who has, this condition, Lyme issues, or whatever, chronic fatigue, or or for exercise, we just start to see just this kind of bell curve, like these people seem to benefit more. Then as researchers, we can look at that and okay, let's do a real clinical study and see if we can really demonstrate that phenomena is occurring.
Right? Can we replicate it?
Yeah. Can we truly replicate that phenomena, or was that just a product of right? Now we can do a double-blinded, placebo-controlled, preferably crossover design that's been randomized and everything. Then we can demonstrate it, and then after that, well, not necessarily be after that, but then of course trying to understand the actual mechanism, like the primary targets of hydrogen gas. It goes in there and it activates this portion or protein or whatever, and then we can start seeing the effects after that. That's how science progresses, and that's what we're trying to do right now.
I love it. And so in these last couple minutes here, as we bring things in, there's a lot of people that are also tuning in to hear how you break through plateaus. So those of you guys that are interested in molecular hydrogen, we'll link to Tyler's Molecular Hydrogen Institute. We'll perhaps link to his presentation if he's generous enough to share that he just did at the Regenerative Medicine Conference, which was fantastic. And we'll put in anything else that we've mentioned, TRUCY-wise or otherwise, in there that's relevant. But you were sharing some fascinating stories about how you've been breaking through plateaus recently, and you're running and you're lifting. So let's use the last, we'll call it 3 minutes, to give the listeners a little bit of a sneak peek and perhaps some suggestions that they may or may not want to apply for themselves.
Right. Well, it's kind of dangerous, but
so don't try this at home.
Yeah.
This is not intended to be medical advice. Please consult your physician before beginning this or any other exercise routine.
Thank you for the disclaimer. That's right. And I'm no doctor, so
yeah, there you go. Take that with a grain of salt.
But I have been doing trying to train and trying to do things really nice and gradual, both in strength training and also with running. And so I thought, okay, I'm going to just be really easy, take things really nicely, and just mildly stress my body so I can maintain that hormetic effect.
Which is the approach that I usually take too. Right. Part of why I'm so fascinated by what you've been doing.
Yeah, so just go and just gradually increase. And so I did that, I've had this experience many occasions and in different areas, both in weight training, both in even fasting. I used to have a hard time fasting for more than, say, 14 hours. Like, it would just be like, I'm hungry, I don't want to, what I mean? Like, I would still fast like once a month for 24 hours, but it was hard. Right. It was still hard. Yep. So in so many different areas, I use these exact same principles, which I'm about to share. Like, can you paint me for this? I'm just kidding. I'm on
the edge of my seat.
I know, it feels like it might be bigger than it is, but I'm just, these are things that I've applied and employed, and it seems be effective.
Well, I've noticed the same scenario that you described, which is trying to gradually increase. I'm even when I'm consistent 3, 4, 6 days a week, I'm like, I'm not really
to get
feeling
those
like
gains, yeah.
And
it's
like,
almost
it's like
always
some
hard.
days are better than others.
Yeah.
And it doesn't really seem to uptick.
Well, that's what happened. My running, you know, it was just every day I'd go out and I'd run, like, I just want to run 10 miles every day as an example. But every time I would do that, it was just hard. It always just felt hard, you know. Same thing with the, you know, bench press. I was like, well, I'm going to do, you know, sets of 10 at 225, perfect form, ready to go. And it was just always really hard. I just barely get it, you know. And same thing with like the fasting I mentioned, and the other examples I could give. Then one day, on different occasions, I thought, you know what? Forget it. I'm just gonna go all out. So like with the fasting, I just went 5 days without food. You know, I just tried. I was like, I'm not gonna eat anything.
What was the decision that you made in your mind before that?
Oh, I really started getting into autophagy and understanding all these benefits and things, and I was like, oh my gosh, I'm missing out on this. And now I understood it. I understood the science, and I understood how to do it. And so I was like, I'm gonna go out this.
So you knew like why you were fasting
Yes.
to a much more impactful
Yeah,
degree.
on a scientific level, so that I could actually apply the principles correctly and not actually hurt myself. Because I swear, before, when I would fast like 24 hours, my strength and my endurance, like everything would just plummet. I mean, my bench press would decrease. When I'm at my max, my best, right? I fast 24 hours. I come back the next day, like I work out Friday, then I fast like Saturday, Sunday, 24 hours. Monday, work out or something. My bench press would go down like 50 pounds, and it would take me a week and a half to kind of get back up there. Like that's, when it was so like, you know, 340 pounds, and then it would be down to like 290 would be hard for me. You know,
what were you doing wrong?
With the fasting,
Yeah.
I don't know that I was doing anything wrong, but my body was not fully adapted.
Okay.
But once I changed, and the same thing with the miles, the 10 miles I was doing, and the same thing with the fasting. So one day I just did a 5-day fast, and then all of a sudden, I'll fly. Like when you fly, you get a lot of radiation damage. One of the best things to protect against radiation is fasting. So I'll fly. I fly all the time to China, Japan, and present at conferences and do research over there. And so I'm on the plane, and I'm just not gonna eat. And so I'll go like 40 hours with no food. And I'm totally fine. Like it's no problem anymore. And even my runs, like today, you know, I had eaten for what, like 16 hours or whatever, and then I went on that, you know, 15-mile run, and then I was 4 more hours, and then before I ate, you know, again, I felt totally fine because I just forced my body to do that 5-day fast, and then I tried to maintain. Okay, and then I did intermittent fasting. You know,
So
14
then
hours.
all of the 24-hour fasts were much easier.
So easy. So easy.
Pushing yourself once
to a harmful degree, but not so harmful that it's, you know, detrimental, like really detrimental, right?
So you can still recover from it. How'd you do it with your running?
So the running, same thing. I was kind of getting this plateau, and I'm like, dude, I'm so sick of this. Like, it's all in your freaking mind. Just get out there. Like, when you get into the zone, like that's the level you have to be at. You just got to go. And I said, no, I'm just going to run. And so I just started out and just ran. I was like, I'll just do 15 miles, you know? I was doing like 60 miles. Like, I'm just going to increase it. So I did 70, then 80, then I did 90 miles, you know? And
Per week.
Yeah, I just increased it like that. And I was hurting. I was sore. I was worried about I was going to get injured. I was pushing myself to the limit. I was down in a bunch of hydrogen too because I was like, I don't know about this. This is the stupidest thing I'm doing. But, you know, I want to get back to my high level. It's like, this is what it takes because I have to be there. And then after I got to those high levels, and then I kind of recovered a little bit.
How long did you do that for?
It was like it was a period of 3 weeks. I just
3 weeks.
went,
Okay.
you know. And the same idea, you could just one day I'm gonna go run a marathon, and you have to be careful you don't like rhabdomyolysis or something, but you could just do that. And the example I gave you, if you did like a 5-mile run,
assuming no biomechanical issues or
yeah, exactly,
issues
right?
and everything like that.
You take a guy do 5 miles, right, and it's gonna be hard for him, and then you have him do like a marathon. Just go do that marathon, as long as it doesn't get rhabdo or something like that.
Even
and
a half marathon in that case.
Yeah, well, so he does that. They'll have him just recover for 2 weeks. That's really not enough training to really induce mitochondrial biogenesis and all these cellular changes and stuff. But something happens. He comes and does that 5 miles, 2 weeks after that. It's going to be like so much easier for him. Mm-hmm. So I just had noticed, I did the same thing with lifting weights, deadlift, bench press, pull-ups, all this kind of stuff.
Yeah.
I just stressed the crap out of my body, just out of my muscles, just tear it, and but you had to be at that safe level.
Meaning using like negatives where you're putting on more weight than you're using.
Huge amount, yeah. Same thing with the pulse. I put on. So I wanted to get my pulls. Like I want to be able to do 2 or 3 in a row, and I was just always struggling with one. I was always struggling to get 1-arm pull-up. I'm like, dude, forget this. So I put the where you can put your legs underneath, and I grabbed the thing. I had somebody help me. I put a bunch of weight on that. I had 220 pounds.
So on the lat pull down machine?
On the lat pull down was just one thing, 220 pounds on that. And I would have a guy help me pull it down, and I would just hold it with one arm as hard as I can. I was like, oh, come on, you know? I love it. And I just like, I have to get over this plateau. So then after I recover from that, all of a sudden one arm pull-ups, I'd be like, what the heck? This is like freaking easy. Like, why was this so hard before? So I just had to get over that plateau. Same thing happened with running. And so there's like this I was showing you that diagram.
Right, yeah. Explain the diagram as we wrap up. I know we're a little bit over time, but I'm enjoying it.
Well, just this idea that you have this circle of comfort level, right? And the radius is only so high, depending on your fitness level. And then the greater circle around that, and then you have a small, radius between that one, and that one is kind of your stress, your beneficial stress level. Typically, that's what you train in.
Call it hormesis.
Yeah, that's your hormesis factor, if you will.
Your good stress.
Before you start harming yourself. Then you have the harmful circle around that one. And you got to be really careful getting that. You get into that with races, when you're really competing and out there. Then you have a bigger circle, which is like death. Like when you cross this line, you literally are killing yourself, and you might die actually when you reach that full 100% of what you got, right?
Right.
And so I'm always in this comfort circle, and then I was like, I'm just in this just mild hormetic beneficial stress circle. But that's not making everything bigger. I've got to get everything bigger. Everything's got to get bigger. And so what I decided to do is like, I'm just going to push out to this harmful stress, maybe even verge into this almost death circle type thing, right? And I did that with all these different things. Of time. For a short period, just one time, and
still listening to your body, making sure you'll be able to
recover.
Making
sure I don't actually really hurt myself.
You're not running through your knee aching.
If it was that, I don't know. Although there are stories of people who have done that kind of stuff, where they've like done an ultra marathon, they've run 100 miles, they didn't train at all, and just totally injured themselves, and then
of course
they do it again, and then all of a sudden they're like way better. There's so many stories of people doing that. They breaking through the wall. They're just like, there's something psychological, something the body, you get that in tune. When you push that level, there's something that happens, and I felt it when I go up like this and just push it to that harmful level.
That's
fascinating. Break through those plateaus.
Last bit, how'd you do it with your bench press?
This is crazy because I have a master's in exercise sports conditioning. You've got to have good form. It's really important. You don't get injured, blah, blah, blah. We all know this. But one day, I was struggling. Like, I wanted to get my bench way, past 315. I wanted my max was 345, and I just wanted to get up there.
And how much do you weigh right now?
Right now, 148.
So you weigh 148. Your max is 345.
Well, yeah. That right now my max is probably 290 or something. I have to specifically be training to be hitting that, and right now I'm focused on running. But what happened was, because I go through these cycles where I'll focus on weights and then I'll focus on running. I always do both of them, right? But there's always a focus, right? I just kind of try to do this thing.
To honor all is to honor none.
Yeah. So this time it came out, I was like, okay, time to focus on weights, and I was like, I'm gonna do everything just really perfect form. My butt's on the bench, just perfect everything, in this powerlifting form, not bodybuilding stuff. Like, I like to lift heavy. I just like that feeling. I just like to lift heavy, whatever I do. I don't care to be really big. I just want to
Yeah.
And so. But I got it to the point where I was doing sets of 10 at 225, and I was there for 3 months, and I just was not improving at all, and it was frustrating because before I could do 265 for sets of 10, and I'm like, what the heck? I just cannot get through this. And when I was so frustrated, I was like, I'll forget this, and I just decided I was bouncing, my belt was off the ground, I was like, whatever,
You threw your form to the
end.
Yeah,
I threw my form. I was like, forget this. When you're wrestling, because I wrestled and stuff, and when you're in
You were state champ in high school?
Yeah, I was. Yeah, that was back in the day. Although I did just wrestle this high school, that was a lot of fun. But anyway, so I was like, I gotta just get in this.
And you realize in wrestling that you're very rarely in perfect
in this perfect form, yeah.
You're getting thrown off balance. You need to prepare for different scenarios where the body's out of
scenario, right.
And you're saying, all right, if I believe that my body's resilient and this isn't going to injure me, I'm going to test using a higher weight, even if it compromises.
Yeah, because my body was already prepared. I've been doing this for a few months, if you will. I'm very much aware of how much weight this is, and so I did that for 2 weeks.
Just increasing your reps?
Just going faster and just pushing it all the way through and getting everything. All of a sudden, I went up to 4 sets of 10 at 260 with the crappy form, but then I could go back and I could do 235. No problem, easy, just nice and slow, la la la, And I'm like, that's so interesting, So it's just pushing these areas, and the same thing with like really heavy eccentrics, like just loading that thing up and just,
and then having your buddy rip it back up.
Right, all these different things. You got to be careful because you can tear, or the Smith machine. You can tear muscles and all this stuff. You've got to warm up. You take various precautions and things, but if you want to be the elite level, you've got to do that kind of crazy stuff, and you will risk you run the risk of hurting yourself. It's not the best way to stay healthy and live longer, but there's something about being at that elite level that
as soon as you get out of bed, you run the risk of hurting yourself.
Yeah,
right?
you do, and I enjoy being on that competitive level. I mean, I'm not the best athlete in anything, but I try to be as well rounded as I can. And
your numbers are pretty impressive, man, and you know your stuff, and I think people will really value some of the knowledge you shared in this podcast. I've had a blast.
It's fun, man.
Thank you for hanging out.
Yeah, no problem.
Tyler LeBaron, where can people stay in touch with? Where can they follow the things that you're working on and stay in touch with you?
Well, I'm not so much of a social media person. I know everyone's saying, Joe, how do I follow you? I do have a Facebook, and everyone's welcome to add me on there. I'm not so good at always getting back to messages because I get so many messages. Yeah, just Tyler LeBaron.
Okay.
I after talking with you, I'll probably try to get more out there to get some of the articles we're publishing and some of the things that we're doing out there through social media. But right now, you're welcome to add me on Facebook and
on the book face. What about where do you do your stuff with the Molecular Hydrogen Institute?
So I'm based in Utah, and then I collaborate with groups all over the place. So actually, like we actually got I'm part of the Slovakia Academy of Sciences in Slovakia, and we got a $250,000 grant to do research on. We're doing a heart transplantation in pigs. So anyways, there's a lot of really cool stuff going on, but I'm able to collaborate with people all over the world on this. So
Tyler LeBaron, it's been a pleasure, my man. We'll link to all of your resources and social in the show notes.
Awesome,
Appreciate
man.
you, bro.
Thank
you.
Yeah, no problem.